Welcome to Let's Get to the Marks, going through a quick A-level chemistry video on halogenoalkanes and halide ions. Don't forget at the start of each part to the question, pause the video, have a go, then unpause to watch the walkthrough. Alright, let's get into it. Concentrated sulfuric acid reacts with alkenes, alcohols and sodium halides. Name the mechanism for the reaction of concentrated sulfuric acid with an alkene. So what you need to be thinking about here is what's going to react with an alkene. Remember, with an alkene you have a double bond, so we're looking at that electron rich area of the alkene being attacked. What kind of things like to attack electron rich areas? They're going to be electrophiles, and of course alkenes undergo electrophilic addition. So for 2.2 it's worth 4 marks. Outline the mechanism for the reaction of concentrated sulfuric acid with propene to show the formation of the major product. So this tells us that there's two products that can be formed, a major and a minor product. And propene obviously has 3 carbons, so we start by drawing that, whacking the double bond in. So here we've got propene. Obviously we've got the double bond, which is electron rich. This is the area which can be attacked by an electrophile. What's our electrophile? Well, we've got the concentrated sulfuric acid is acting as the electrophile here. And it's the fact that the OH bond on sulfuric acid is polar. You need to learn how to draw the displayed formula of sulfuric acid out. That's probably a really tricky part. If you don't revise it, you won't know it. So learn this way of drawing the displayed formula for sulfuric acid. The delta positive hydrogen, does it go to the electron rich area? No, it's always a pair of electrons that come from the double bond to the positive. Remember, electrons only can move. So we want to get our first mark for a curly arrow from the double bond to the delta positive hydrogen, and the second mark to show the bond breaking. You must touch your curly arrow to the bond, and then it must point towards the oxygen atom. Now we're going to draw the intermediate. We've scored 2 out of 4 marks already. So here's the choice where you can have a major or minor product. The hydrogen atom here I've circled in red can either join to the first or second carbon around the double bond. So the question is, which carbon atom, number 1 or 2, does that hydrogen atom join to that I've circled in red? That's the big question. Which one would it join to? Well, if it joins to the second carbon in the middle, then we'll only get 1 alkyl group. If it joins to the last carbon or the first carbon here, then we get 2 methyl groups on the sides, and which is where it joins in the major product, and that will leave our carbocation looking like this, with a hydrogen with a positive plus charge on the middle carbon in the old propene molecule. And then we need to draw a curly arrow from the pair of electrons to the positive charge. Don't forget, with your lone pair on the oxygen atom, we need to put the negative sign as well, otherwise you won't get that M4 mark. Now that's all 4 marks, but I'm going to show you the minor product because it helps with your understanding. So the other type of product that this could form, the other carbocation this could form, is if the hydrogen that I circled in red, I'm circling here, joins to the second carbon, the middle carbon. That would leave the last carbon or the first carbon as the positive carbon atom. However, this only has 1 alkyl group. It's got that ethyl group, C2H3, and that means it's going to be less stable, whereas our major product has 2 alkyl groups, 2 methyl groups, whereas our minor product only has an ethyl group or 1 alkyl group. And the more alkyl groups or R groups you have, they're electron donating, they stabilize the carbocation and make it more likely to form, which is why our major product had 2. 2.3, draw the structure of the minor product of the reaction between concentrated sulfuric acid and propene. So we've kind of just done that. We really want to just draw the minor product. So that's the one which has the kind of ethyl group instead of the 2 methyl groups. So what we're going to do, we're going to sketch that out here. So notice in the minor product, the positive carbon is this one. It only has 1 ethyl group. So that oxygen is going to donate its pair and form a covalent bond to that carbon here. And then we just need to fill in the rest of the structure, which is that sulfate group there. And there we go. 1 mark. That's the minor product. Okay, 2.4. Explain why the product shown in your answer to 2.2 is the major product. So why is it that the major product forms? And I've kind of already gone through this, right? So we're going to draw this out again just for the sake of it. So here is the major product. of course, it had the carbocation had the positive charge on the middle carbon. That enabled it to have, I'm circling them here, two methyl groups. Both those methyl groups are electron donating, or they have an inductive effect. They kind of push their electrons onto the positive carbon atom that this oxygen is joined to, and they stabilize the carbocation. It means the carbocation intermediate is more likely to form, meaning that this is the only, or this is the major option. And so all of the marks formed here are for basically saying it's got two methyl groups or alkyl groups. That's one mark. Whereas the minor product only has one. These alkyl groups are electron donating, or they have an inductive effect. Stabilizing the carbocation is the second mark. Whereas let's check out the minor product here. Look, this is the minor carbocation that will form to make the minor product. It's only got that one alkyl group, and so has less of an inductive effect. Means that this carbocation is less stable, so is a less likely intermediate to form. And here we go. Okay, we're on to 2.5. Butan-2-ol reacts with concentrated sulfuric acid to form a mixture of three isomeric alkenes. Two of the alkenes are stereoisomers, so they've told us we've got two stereoisomers. You remember cis, trans, EZ, they're your stereoisomers. Draw the skeletal formula of each of the three isomeric alkenes formed by the reaction of butan-2-ol with concentrated sulfuric acid. Give the IUPAC name of each isomer. Okay, so what we have to think about here is butan-2-ol. What kind of alkenes can butan-2-ol form? Well, it can form but1ene and but2ene. That's all it can form, because the double bond is butan-2-ol can either form on either side of the carbon with the OH group. So we're going to have but1ene is one of our answers. And the next answer is going to be but2ene. But we can get two different versions of but2ene called stereoisomers to see if you can work out the two different stereoisomers. So I'm going to draw out the molecule here. Look, here we go. We got but2ene, of course. And what can happen is the two methyl groups can fold round with but2ene to be on the top. What do we call this? Hopefully you know what this is. It looks like cis, but we actually use Z for Zusammen, which means sisters. So when you get the two methyl groups or two hydrogens next to each other on one side of the double bond, we call that a Z isomer. So this would be Z-but2ene. And there's the skeletal formula for it. So the other version of this is where we have a methyl group on both sides of the double bond, or you could say a hydrogen on both sides of the double bond. And the word for this is Entigen, and it means opposite. And so Entigen in German means opposite. The different groups are opposite each other across the double bond. Of course, you have to have a double bond for these EZ isomers because there's no rotation around the double bond, so they can permanently get stuck in that configuration. And this would be E-but2ene, and this would get you 3 marks. You need the skeletal formula and the full IUPAC name for each of the marks. Moving on, we're nearly there, peeps. 2.6, a byproduct of the reaction between butan-2-ol with concentrated sulfuric acid has the molecular formula C4H8O. Name this byproduct, identify the role of the sulfuric acid in its formation, and suggest the name of the method that can be used to separate the products. And again, it's another 3 marker. So if we draw out the formula right, you've got butan-2-ol. Of course, that's a secondary alcohol. So what's the byproduct going to be? Secondary alcohols can be oxidized to ketones. And so when this is oxidized to a ketone, it's going to form butan-2-one. Sulfuric acid is the oxidizing agent. And how to separate the butan-2-ol from the reactant, the butan-2-ol, okay, the alcohol and the ketone, you'd use fractional distillation, which is where you rely on them having different boiling points to separate them. 2.7, concentrated sulfuric acid with solid sodium chloride. Give the observation you'd make with this reaction and state the role of the sulfuric acid. So this is an equation you need to know off by heart. It's part of your AS unit, which carries on over into A level, obviously, your group 7. It's part of your halide ions and looking at their reducing effect generally. So what we get here is sodium chloride plus sulfuric acid makes sodium hydrogen sulfate and hydrochloric acid. Now the observation is going to be misty fumes, and the misty fumes is the hydrochloric acid, or sorry, the hydrogen chloride gas. It's not actually an acid unless it's dissolved in water. Now, what is the role of sulfuric acid? Well, if you check here, none of the oxidation states, so it's definitely not redox because chloride ions aren't a good enough reducing agent. So it's not redox. So what has the sulfuric acid done? Well, it's lost a hydrogen. Look, it's gone from H2SO4 to HSO4. That means it's acting as an acid. It's donated a proton, hasn't it? The chloride ions in this situation are acting as a base, or the sodium chloride is, because it's accepting a hydrogen. But here it's asking us about the role of the sulfuric acid, and of course, it's a proton donor. Concentrated sulfuric acid reacts with solid sodium iodide to produce several products. So this time we're looking at solid sodium iodide, and they want to know the black solid, yellow solid, and the gas. There's about 3 different equations you need to know for iodide ions. They are better reducing agents than chloride ions or bromide ions or fluoride ions. And first up, the reaction is, again, not a redox one, the first one, but it forms hydrogen ion. Now the hydrogen iodide reacts with the sulfuric acid in a redox reaction. We know this is redox because of the change in state of the sulfur when it goes from sulfate to sulfur dioxide. But the black solid formed here is the iodine product. So iodine is the black solid. Now we get a yellow solid. You can probably guess what a yellow solid is. You should know a non-metal yellow elemental solid. We've got sulfuric acid here, so there's a nice little clue there. And then we've got the bad smelling, eggy smelling gas. And this reaction here shows that the iodide ions are such good reducing agents, they can further reduce the sulfur in sulfur dioxide to hydrogen sulfide, where it is way down to it's been reduced even further. And of course, the yellow solid is sulfur atoms represented by S. I haven't written the reaction there because I ran out of room. And that's the end of that. So the bit of your revision guide you need to look at, I'm going to show you, okay, is here. So let me just clear the screen. Okay, this is from the brilliant CGP revision guide. Of course, it doesn't have everything you need, but it is still a great resource. It's what I often use. And this little chapter in the revision guide on the halide ions and their reducing power shows us that fluoride and chloride ions aren't strong enough reducing agents, but the bromide ions are even stronger and can form more products. And then the iodide ions are the strongest reducing agent out of the halide ions. And you can see all the different reactions you need to know off by heart. And really, you just need to put the hard work in and you need to learn those off by heart using revision cards. Anyway, guys, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks.
You're still here? It's over.